Hi guys! We've used the patented Shoto Lab system to control various laboratory processes in our development work. We've used it to run and control distillations, both simple and fractional distillations, and to control a variety of reaction setups. Our current development process was the coolest setup so far, and we decided to put together a video showing the power of the Shoto Lab control system. It will show how the Shoto Lab system can independently control 4 catalytic gas phase liquid reactors. You will see for yourself how the capabilities of the Shoto Lab system can transform your fume hood into a modern-day computer-controlled pilot plant.
Here's a picture of the hood with the setup showing from left to right the 24-volt DC power supply used to operate the heaters, gas cylinders to charge the reactions, the 5-position reactor setup, 3 manual flow controllers along with 4 electronic flow transducers, the Shoto Lab system, and the computer is off to the side so you can't really see it. In the back are 4 PVC cylinders to hold the gas for each reaction, 4 flask and condensers to collect the product, and a manually controlled Masterflex pump with 4 heads attached to recycle unreacted gases. Each of the reactors has a thermocouple made with thermocouple wire, a flow meter, pressure transducer, and a light sensor to monitor the reaction progress. You can watch our individual video showing how each of these components was connected and configured to the Shoto Lab system. The greatest benefit of the Shoto Lab system is it allows you to use these sensors without the need for any other controllers or meters. It allows the use of sensors at about 1/10 the cost of your traditional lab sensors. Here's an example of the tube reactors used in this setup. As you can see, it has 2 1/4-inch spade terminals attached to 15 thousandths nichrome resistance heating wire. The reactor has 2 number 7 ace threaded inlets. One contained a thermocouple and a pressure transducer, and the other one was used for recirculating the gas for the reaction. If I turn the reactor over, you can see the light sensor attached. I'm using it to determine when the reaction is completed. This reaction turns clear at its endpoint, and instead of using my eye to guesstimate the time when it was done, the sensor will tell me exactly when each reaction is done. The spade terminals were connected to a 24-volt DC solid-state relay, which were controlled by the PIDs in the Shoto Lab system. The nichrome wire was further wrapped and insulated with 1/4-inch ceramic braiding to protect the heat resistance wire from abrasion. The ends were capped with heat shrink to keep them from fraying. This is the first time I used this reactor, and they really worked great. I was really impressed with how the system worked. Here's a top view of the reactor showing the pressure transducer, the thermocouples, the gas inlets and outlets, and how everything was connected. Here you can see the flow controllers with the flow transducers mounted on the back. Since we only had 3 flow tubes, I'm using a valve and electronic flow meter for one reactor. You can see I'm using 2 TC boards instead of the typical TC and SP board that are normally sold with the system. Once everything was connected, here's how easy it is to configure the Shoto Lab software. When you open the software, here's the first page you see. It's the information page. It allows you to enter general information like the experiment name, your name, notebook information, the purpose of the experiment, and you can also put in a complete description of the experiment setup as well. After entering the general information, go to the channel setup page to configure all the channels of the Shoto interface boards being used. My first connections were the thermocouples, and I attached these to the first TC Shoto Lab interface board. Configure them by typing in their names. The first reaction is temp 1, the second reactor is temp 2, the third reactor is temp 3, and the fourth reactor is temp 4. I also installed a thermocouple for ambient temperature reading, and I'm going to input that as well. Next, select the type of thermocouple you are using. These are all type Ks. For me, it's easier and faster to work from top to bottom. I also like to add another decimal point reading to the temperatures. I know thermocouples aren't that accurate, but the extra number is nice to see at times. Finally, activate the channels. To show the readings, just simply push the buttons. And now you have the temperature reading showing. My next sensors were the opacity meters. These were connected to the single-ended inputs on the first TC Shoto Lab interface board. And just like the thermocouples, first name the channels, I'm going to keep things simple and follow the same routine as with the TCs. The first reactor I'm going to call opacity 1, the second one opacity 2, the third one opacity 3, and the fourth one opacity 4. Since I'm reading voltages on these, I don't have to change the channel type. And the maximum voltage that these will read is 1.25 volts. So let's change the gains to get the best reading. Change the sample time to 100 to match that of the TCs. Change the decimals to be displayed to 3. Now activate the channels to get the readings. Now I'll configure the second TC board by scrolling down to the next TC channels. I connected the pressure transducers to these channels. And again, let's name them accordingly. Pressure 1 for reaction 1, pressure 2 for reaction 2, pressure 3 for reaction 3, and pressure 4 for reaction 4. Since these are differential voltages and not thermocouples, leave the settings as is. The maximum voltage output from these pressure transducers is 0.125 volts, so I'm going to configure the gains accordingly. I'm also going to set the sample time to 100 to be consistent with my previous settings. And again, change the decimals from 1 to 3. Next, turn on the channels by pushing the activate button. It'll turn from red to green as you see. And pressure transducers need to be calibrated, but we'll do that a little later. The next channels are the flow meters. These were connected to the single-ended inputs on the second TC board. As above, just name the channels. Flow 1, Flow 2, Flow 3, and Flow 4. Let's stick with 3 decimals. The output max is 2.5 volts, so we'll keep the gain as it is. And again, stick to the same sample time of 100 for all of the channels. And now activate the channels. As you can see, the second reading isn't reading correctly. Let me take a look at it real quick. The connector was loose, and that fixed the problem. As with the pressure transducers, the flow meters need to be calibrated, and let's do that real quick. The spec sheet says that these flow meters read 0.5 volts at 0 flow and 2.5 at 100 cc. To calibrate them, click the Edit Scaling. As you can see, the first flow meter is reading 0.629 at 0 flow, so let's enter that. The Y value is 2.5 volts at 100 cc, so let's enter that. And click OK. Click the second flow meter. That's reading 0.5057 at 0. Again, let's enter that and keep the 0 at 0. They read 2.5 volts at 100 cc, so let's enter that. Click on the third flow meter. You see that that's reading 0.493 at 2.5 volts. Let's enter that. And click OK. And finally, the last one, the fourth channel, is reading 0.507 at 0 flow. And as the other ones, 2.5 volts at a full value reading of 100 cc's per minute. Let's type in the units for all of these. cc's per minute. Finally, you have to configure the PIDs. To do this, click on the Control Output tabs, click the wrench, and here you see all of the control options we have. These work in conjunction with the Shoto Lab power supplies. And in this reaction, we're going to be using the PIDs, so click that. For heating mantles and resistance heaters, experience has shown that 8 is a good p-value or proportional gain value. And 10 works for the integral value, so type those in. And keep 0 for the differential value. Repeat this for the second channel, but this time you need to change the reference channel to the second reactor. This is the temperature the PID will be using for monitoring. You can keep everything else the same and press OK. Do the same for the third reactor. Again, change the analog input to the third reactor thermocouple. And again, everything else can be kept the same. And finally, the fourth channel. Click the wrench, choose PID, select the correct reference channel, and that is the fourth reaction temperature, and click OK. Let's click the box to display the status. This will show the lights on the display page. I forgot to name the channels, so let's go back and do that now. The first one is heat 1, the second one is heat 2, the third one is heat 3, and the fourth one is heat 4. For consistency, let's make the first one the same format as the others. Let's change that to smaller letters, heat 1. And now you're all ready to run. To do this, go to the display page. Let's plot all the same channels on separate plots. This makes it easier to see what's going on. So click on plot 1, name the plot pressure for this case, select the channels to plot, choose the 4 pressure channels, move it to the side where you can see it better. Let's move it out of the way so it's easier seen. Next, plot temperatures, select plot 2, let's name it temperatures, press OK, select the temperature channels to plot, and again press OK. Next, activate the PID channels by going to the setup page, click the buttons to activate them. And let's make plots for the other sensors. Let's do the opacity sensor real quick. Click plot 3, name the plot name opacity, click OK, and again select the channels to plot. Let's repeat the same for the flows. Click plot 4, name the plot flows, click OK, select the channels and pick the 4 channels you'd like to plot. Now let's set the PIDs to the temperatures we want. The first one's going to be at 60 degrees, the second one at 70 degrees, the third one at 80, and the last one at 90 degrees. You can see that the heat lights are indicating on now, and it should be heating up. And I don't want to waste 4 hours of your time watching this, so I'm going to speed it up relatively quickly, and you'll be able to see how the Shoto Lab system runs. I'll put some comments also on the screen as it runs so you can see what's going on. Well, that's a brief description of the Shoto Lab system. Thanks again for watching.